All right, now we're going to talk about ionic theory. What happens when chemicals are dissolved? Lots and lots of what we're going to do in this class and when a lot of reactions just in general occur in water. So we said that that was aqueous. Here's the AQ. If you put an AQ after a substance, that just means dissolved in water. So we can write the equation. If we write the molecular equation like that, what I'm saying is that this CaCl2 is dissolved in water, the AgNO3 is dissolved in water, and the calcium nitrate is dissolved in water. Now this is solid, so that means it's not dissolved in water, but it's actually a solid. So what happens is we have a beaker, and before we that's not very good. Before we have anything in there, we have the two solutions that are aqueous. So we have some liquid in there, and then we pour in the second liquid. I'm not very good drawing. So we pour in the second one, and then after they're poured together, we end up with a solid. Let's pick a different color here. A solid that kind of ends up on the bottom. So it's not dissolved anymore. So that's what the S is. So that's, if you're reading an equation and you see that, that's what you can tell. What does it mean for an ionic species to be dissolved in water? Well, what happens is the ions actually pull apart from each other. So let's look at that. So we call that dissociating. So an ionic compound dissolves in water, it dissociates, or in other words, breaks apart into independent ions. So a very simple example would be NaCl. If NaCl is solid and then we dissolve it in water and it dissolves, so it's aqueous, now the sodium ion separates from the chloride ion, and so we write them separate. Now, you might see sometimes when the AQ is not listed, if you see the ions separate from each other, separated from each other, that tells you they're aqueous, so if they're in solution. But a lot of times we'll put that in for emphasis. Sometimes you'll also see like NaCl. Oh, let's not do it there because it's going to show up. You might see NaClAQ. If I saw NaCl and I saw this, what would that tell me? That would tell me that I have the Na plus and the Cl minus, that they're separate from each other. Let's look at another example. So this one's a little bit different because notice that I have two Cl's here, right? So when they break up, I've got a Ca and a Cl and a Cl. And they don't hang out, the two Cl's don't hang out together. So this is going to break apart. This is going to break apart. This is going to break apart. So I'm going to have the Ca, and I'm going to have a Cl, and I'm going to have another Cl, and they're all going to be separate from each other. So this is how I write it. I write the Ca, and there's one of them. And now there's two Cl's, so I'm going to write them as separate entities. So the 2 actually comes out front. There's two Ca2, there's one Ca2 plus, and there's two Cl minus ions. So this is how you would represent that. If you have, I don't know what else I have on here, but if you had a polyatomic, let's write it here. Like if you had NaNO3, when you dissolve that in water, the Na, now the polyatomics always stay together. So this would be written as Na plus NO3 minus. So that's why I really recommended at the time that you really learn those polyatomics, because they're not going to break apart anymore. They're going to stay together. And it can get really confusing. So the polyatomics on the little subscripts on polyatomics don't come out front. So it gets very, very confusing, and I understand that. So for example here, if it helps you, draw your polyatomics in parentheses. So now you can kind of see there's one of these, one sodium and one nitrate, as opposed to something like, let's think of another one like let's see, calcium hydroxide. If this was soluble, then And I don't think it is. Let's not confuse the issue. Yeah, calcium. No, let's not confuse the issue. Let me come up with a different one. I know. Well, yeah, let's see. Let's just do this one. So Ca2, oh no. Ca NO3, 2. There we go. If we had calcium nitrate, now you can kind of see that there's 2 sodiums and 1 calcium. So we would draw that as calcium plus 2 nitrate. So now that 2 does come out front, but the nitrate. So really learn those polyatomics. If it helps you to just kind of cover it up with your thumb or something to see, well, whatever's in there, there's 2 of them. We don't change whatever's in there. It's a polyatomic. Let's erase some of these. So these compounds that freely dissociate are called electrolytes. They're ionic in solution, and they actually conduct electricity. And so that's the real reason why you don't want to be in the bathtub with your hair dryer, because water itself actually is not very conducting. However, it's the negative charge particles in water, which are always, there's always some. There's some sodium, there's some chloride, etc. So there's a lot of it. Okay, so this is technically a molecular compound. It's not ionic. Ions are always made of a positive ion that's not hydrogen and a negative ion. So because hydrogen is the ion here, we wouldn't consider this a salt, but it is ionic when dissolved in water, and it will break up into its ions. So again, this would be an electrolyte. It's because it's electrically conducting. And then on the flip side, we have some compounds that dissolve but do not dissociate. So a lot of molecular compounds, if they're not ionic, we talked a bit in the last chapter, chapter 2, I think. Remember that a molecular compound is generally made up of nonmetals, whereas an ionic compound is made up of a metal and a nonmetal. So molecular compounds will dissolve but not dissociate. So an example of that is glucose. So we know sugar can dissolve in water. However, it does not dissociate because it's not ionic, it's molecular. So what happens is, if we just write aqueous here, we just mean it's dissolved in water. You take sugar and put it in water. So we would call this a non-electrolyte and non-conducting because it's not ionic at all. I may do a separate video with this. This is just a little simulation, and I think I might have one, but I'll post it separately because I can't go to it on this video. But it's a real interesting. I think you would really get something by looking at this website, which is a simulation, and I will post that. I will do a little video with it and post it later. Now, not everything dissolves to the same extent. So some salts are soluble and dissociate 100%. And some are not soluble and don't dissociate. So the solubility of a compound just says how much does it dissolve. So far, most of the things we've been looking at have been strong electrolytes, which mean they completely dissociate. And so an example of that is our NaCl, completely dissociate. 100 solid NaCl crystals will break up apart into 100 Na plus and 100 Cl negative. So solids that do dissolve in water are considered strong electrolytes. However, we have some that are not. So a weak electrolyte is one that dissolves in water just a very small amount. Sometimes we also call these precipitates because they're solid and they don't really dissolve. So this is not a precipitate example, but NH4OH is a weak electrolyte, and sometimes you'll see it represented like this with a double arrow. So it mostly stays together but it does dissociate to a very small extent with the ions. So we would call this a weak electrolyte. And I'm in a little while I'm going to give you some help recognizing when it's weak and when it's not. We'll talk about the solubility rules in just a minute. So molecular compounds are either non-electrolytes or weak electrolytes. This, again, is a little video you might like to watch, and it just shows the dissolving of salt in water. So what's happening, here's a sodium chloride crystal down here. And what happens is little water molecules have a positive end and a negative end. And so what happens is the negative end of the water molecules are attracted to the positive sodium ions, and they'll come and kind of be attracted to the positive ions. And then the positive ends of water will come and attack the chloride. And so if enough water molecules surrounds this chloride ion and carries it away, and then more water molecules will come in and it'll just kind of carry away the different ions. And this is what it looks like when it's dissolved in water. The sodium is surrounded by a bunch of water molecules with their negative ends pointed toward the sodium, and the chloride ions are surrounded by the water with the positive ends attracted to that. And so this is what it means to be dissolved, or if it's so solvated or dissolved. And so it sort of has to do with the attractions between the water molecules. If the water molecules are pretty good at carrying away the ions, then it's going to be soluble. But if the attraction between the ions is so strong that the water molecules can't pull them apart, then it's going to be insoluble and it's going to stay dissolved. But if you want to watch, if you get on the actual PowerPoint and click on that or type that into a search engine, you can see it's just a quick little video. So like I said, substances vary in their solubility or ability to dissolve in water. So if something dissolves very easily, we call that soluble. And if something doesn't dissolve very easily, then we call that insoluble. So we have actually rules that you can use to predict if a compound is soluble or insoluble. So let's go through these rules. It's on the following table, and these would be something that I would highly recommend learning or at least having available whenever you work these problems. Okay, so this is the solubility rules. So let's kind of go through them. So the first rule is that anything that has group 1A positive ions, so lithium, sodium, potassium, and then including ammonium, NH4, they're always soluble. It doesn't matter what the negative ion is. If one of these is the positive ion, they will always dissolve. There's no exceptions. In a similar way, if you have the acetate ion or the nitrate ion, so these negative ions, no matter what they are paired with, no matter what positive ion they're paired with, they will always dissolve, so no exceptions. Now, if the negative charge of the compound is a chlorine or chloride, bromide, or iodide, they're often soluble. Most of the time they're soluble, but there's a few exceptions, and so the exceptions are listed over here. So silver chloride, mercury chloride, and lead chloride. Silver bromide, mercury bromide. There's two different mercury bromides, and lead bromide. So silver, mercury, and lead tend to be the exceptions to the rule. So you want to keep in mind that these are not soluble. They will not dissolve in water. Similarly, SO4 negative, most of them are soluble, except for, now we add a few more. So we've got the silver, mercury, and lead, and we also have barium, strontium, and calcium. So these 6 are insoluble. All the other sulfates are soluble. Now we flip. So carbonates, CO3 negative 2, most of them are insoluble. So the only ones that are soluble are, going back up here to rule 1, is if they have the lithium, sodium, potassium, I guess technically rubidium and cesium, but these are the main common ones. So the group 1A carbonates will dissolve. none of the others will. Same thing with the phosphates. Most phosphates are insoluble except for the group 1A. The sulfides are insoluble except for group 1A or in the ammonium. And then finally, OH negative hydroxides are not soluble either. And the 1A hydroxides, so sodium, lithium, potassium, and then also calcium, strontium, and barium. These are the exceptions, so these are soluble. So you'll want to kind of have this handy, and again, I may have this is a fun simulation, and I may have a separate video talking about that. So let's do a few practice problems. Decide if these compounds are soluble or insoluble. So Na2CO3. It's soluble because we've got Na, which anything with Na is soluble. Okay, PbSO4. Most sulfates are soluble, however, lead is one of the exceptions. So that is insoluble, not soluble. Most hydroxides are not soluble, and the only exceptions were the sodium, lithium, potassium, calcium, strontium, barium. So cobalt is not an exception, so this will also be insoluble. Now, barium nitrate, all nitrates are soluble, no matter what they're paired with. So right away I can say that's soluble. And then this last one, most phosphates are not soluble, however, ammonium is always soluble as well. That's rule number 1, so this is also soluble. So I hope you follow how to do that, and you'll have to be able to predict. So what does that mean? Remember we saw earlier, if something's soluble, it totally dissolves in water. This can be represented as its ions, so I would write that as 2Na plus CO3 negative 2. So the CO3, one of those breaks apart, and each sodium breaks apart. Since this is insoluble, that means I keep it together. I don't write it as separate ions. This one I keep together. I would always represent it as written together. But the soluble ones in equations, I would write them as separate. This one would have 1 barium and 2 nitrates. Don't forget you have to put the charges or it's wrong. Charges are, you don't write the charges when they're stuck together, but you do write the charges when they're separated. This one also, we have 3 of those NH4 groups that are positive, and then we have, if it helps to put parentheses, there's only 1 of those. So there's 1 phosphate. So that may help you see what we're doing. We're going to get to that in just a minute. All right, so like I just said, we have different ways of representing our equations. Some by putting the little symbols, solid, liquid, aqueous, whatever. And then sometimes, like I just showed you, we represent them as ionic equations. So let's look at an example. So if we have a molecular equation is where the reactants and products are all written as if they were molecules, even though they may actually exist in solution as ions. And so that's where we put the labels. So in this example, calcium hydroxide, aqueous, plus sodium carbonate, aqueous, gives us calcium carbonate solid plus sodium hydroxide, aqueous. And if we go through our solubility rules, we know that most hydroxides are insoluble, but calcium is soluble, so that's why we represented that as aqueous. Here, anything with sodium is aqueous. Carbonates are not soluble, and calcium's not an exception, so that's why that's considered insoluble. And then anything with sodium, again, is soluble, so that's why we have aqueous. So this is one way to represent it, and this is called the molecular equation. So everything's still written as molecules, but you just have which phase, if they're soluble or insoluble, written next to it. But then we can also write this equation by breaking it apart into its ions and showing them actually the way they are in solution. So I just went over that. Okay, so now let's look at it. So if we write the ionic equation, it actually represents strong electrolytes by independent ions. So the calcium, I'll just write it above here. The calcium hydroxide, because it was aqueous, it got broken up into the one calcium, 2 plus, and you do have to remember the charges, and 2 hydroxides, negative. Then we had the Na2CO3. Sodium carbonate was aqueous, and so that breaks up into the 2 sodiums and the 1 carbonate, and carbonate's a -2. Now, again, on the molecular equation, you do for sure need to put down these symbols. On this one, it's not quite as important because you know if it's an ionic equation, then if they're apart, they're aqueous. If they're together, they're not. So you don't necessarily have to put the symbols after these. You can, but you don't have to. So here's my sodium and my carbonate. Now, as I said on the previous slide, calcium carbonate is considered a solid. It's not soluble, and so it's not going to break up in solution. So we still keep it together, because what's going to happen is if I pour the calcium hydroxide, and then I pour the sodium carbonate in, what's going to happen is that the carbonate and the calcium are so attracted to each other that they're going to glom onto each other. And again, they're going to form like a precipitate down here at the bottom. And so it won't be dissolved in water anymore. And that's why we don't write it that way. We write it as a combined. And then finally, our sodium hydroxide, remember it looked like this, sodium hydroxide, aqueous. And so if we do have a coefficient, it distributes. So we have 2 sodium ions and 2 hydroxide ions. So this is called the ionic equation. Sometimes we call it the complete ionic equation because you have all the ions written out that need to be written out. Sometimes you'll see an arrow. You don't usually have to put that, but that just means it precipitates out. Everything was dissolved, and then suddenly you've got a white precipitate well, it doesn't have to be white. This one happens to be white, but it could be colored. So as I said on the last slide, that was called the complete ionic equation. So a complete ionic equation is the equation in which all strong electrolytes, anything that's soluble, will be written separately. So here's just another example, and let's go ahead. I think I have it coming. I don't know why that blue showed up, but anyway, if it's aqueous, we write it separately. So let me go ahead and write that out so you can see the practice. So there's 2 sodiums plus 1 SO4, and SO4 is a -2. And this is aqueous as well, so copper, and it happens to be a +2 because we know Cl is a negative, and if there's 2 of them, that has to be a -2, so copper is a +2. On the other side, we have 2 sodiums and 2 chlorides. I think that's one of the biggest mistakes I see is people not distributing them. And then over here, that's solid, so we keep it together. So actually, I have that written right there, but I wanted to kind of go through it with you. But what I want you to notice here is that there's 2 sodiums on the right and 2 sodiums on the left, so it's kind of like it's repeated itself. So we can actually cross those out. And same thing with the chlorides. There's chlorides on the left and on the right. And so what we have is called the net ionic equation, which actually looks like this. SO4 -2 plus copper. And I think I've said it before, the negative, which if you put negative first or the number first, it doesn't matter. I tend to be really sloppy about that, as long as you have them. So this is called our net ionic equation, because the things that have shown up on both sides can be canceled out. I think that's on the next slide. So the Cl and the Na appear identically on both sides of the equation. They can get canceled out. They're called spectator ions because they actually don't take part in the reaction. So a spectator ion does not take part, they just hang out. So the fact that sodium on the left and sodium on the right is the same means they didn't really participate in the reaction. The chlorine, but now the copper and the sulfate both did participate. So then, like I said, so that was the complete ionic equation with all of them. And then this is the net ionic equation. So that the spectator ions have been removed. Again, please keep in mind that you have to write your charges. You have to, unless they're in a compound. Once they're stuck together, we don't write the charges. Also note that charges have to be preserved, which means that everything on the left-hand side, charge-wise, should equal the right-hand side. So in this case, even though these are separate, there's a +2 and a -2. So overall, this is 0, and overall, this is 0. And so it's balanced. If you end up with some more charges on one side than the other, then you probably haven't canceled everything out. And probably one of the biggest mistakes is not remembering to distribute or pull the subscript out front if there's more than one. So those are common mistakes. Now, if it turned out that every single ion was a spectator, so like if it happened, which is not true in this case, but if it happened that this was also soluble and it was written separate and everything canceled out, then basically you have no reaction. But still take note that if I ask you on a question, I may want the complete ionic equation, and then for the net ionic equation, you would just say no reaction if nothing happened. But do make sure and do all the questions that I ask you to do. So let's do another example. We'll start with the molecular equation. HNO3 is aqueous, MgOH2 is a solid. Now notice this is a liquid. Liquids also, so solids don't get broken apart and liquids also don't get broken apart, but anything that's aqueous does. So let me just go ahead. I know I have it on the slide, but let's go ahead and remember how to do it. So the 2 distributes, and remember that this is a polyatomic. So there's 1 hydrogen and 1 nitrate. So it's 2 hydrogen, and now it distributes, so I have 2 nitrates. This is a solid, so it stays together. And then on this side, that's a liquid, so it also actually stays together. I'll go ahead and put those in. And then this side, this one's aqueous, so I'm going to say Mg. Mg is in the second column, so it's a 2+, and I'll have 2 nitrates, so don't forget to bring the 2 out front here. So now we have, if we look at our spectator ions, this time the only spectator are the 2 nitrates. So let's see what's left over. 2H plus MgOH2 gives me 2H2O plus Mg2+. That's the net, so this is complete. And this is net. And this side, notice that this is not 0 on both sides. However, the right is 0 plus 2. So it's a +2 charge total. And this one is 2 times 1, so it's a +2. And this is neutral. So the charges are conserved. Obviously, you can't have charges hanging out without the counter, but those are the ones that we canceled out. So we're just not worried about them in this equation, but they're there. So ultimately our solutions have to be neutral, but for our equations, they don't have to be. I hope you can see that. So nitric acid and magnesium nitrate are both considered strong electrolytes, so they get broken apart. So I've kind of just gone through it. Let's see what happens there. So if we break them apart into all the ions that can be, liquids and solids stay together. Nitrates are the spectator ions because they show up identical to each other on both sides, so they can be canceled. And then finally, we eliminate those, and we get the net ionic equation, which is also the essential reaction. So these take a lot of practice, and I know on Canvas I have some practice sheets. I would recommend practicing them. They take a little practice. So I'm just going to sort of summarize the steps that you want to do. First, take the molecular equation. Make sure it's balanced before you do anything. Rewrite the equation showing the ions if it's a strong electrolyte. So now notice so far I've always put AQ next to it, but remember that our solubility rules can tell us. So a strong electrolyte means they're soluble. So if it doesn't tell you in the molecular equation, you can go to your solubility rules and figure out if it's dissolved or not dissolved. So using the solubility rules. And then a few of them won't be on the solubility rules, and we're going to talk about that in a minute, the acids and bases, but most of them you can do the solubility rules. Then just identify and cancel spectator ions and rewrite the net ionic equation. Don't forget to distribute coefficients. Also, don't forget to bring subscripts out front, but again, subscripts that are not part of the polyatomic. Right, so just to review, if I have MgCl2, since Cl is by itself, I would have Mg and 2Cl negative. However, if I had MgSO4, notice that that's a polyatomic. I've got one Mg and one SO4, so this would be written as 1 and 1. So be really careful with those. This is everything right here is so confusing. When do you bring that out front? When do you not? So again, highly recommend learning those polyatomic ions so that you can recognize them. And notice in that case, before I did it, there was no parentheses. So sometimes it's easy if you see the parentheses with a number outside it, but if you don't see the parentheses, take a minute to recognize. And if you see more than 2 elements, then there's got to be a polyatomic. So identify it. That will help you a lot.